All right, welcome to the first lecture in quantum computing, Introduction to Quantum Computing. So what is quantum computing? Well, quantum computing uses quantum computers to do computations and algorithms. What is the difference between a classical computer and a quantum computer? Classical computers work with zeros and ones, using transistors as switches. So basically, you can think of like a light bulb, it's on, it's off, and people used to use Morse code to send information by turning lights or sounds on and off. And then we got more evolved and we have switches, transistors at very small scales made of semiconductors. And we use them to uh, create sequences of zeros and ones by turning signals on and off. And then that creates a classical computer which stores information, processes information, allows us to run algorithms using digital gates and so on and so forth. In a quantum computer, we use various types of quantum techniques to create superimpositioned qubits. And so, what we're going to talk about is the mathematical representation of qubits now, regardless of the type of physical hardware quantum computing we are doing, whether it's superconductors or quantum annealing or some other method of doing this. So right now, let's see. So in the classical case, we had the bits 0 and 1. And for the quantum case, we will define the bit vector 0 to be the vector 1, 0, and the vector 1 to be the vector 0, 1. Okay? Now, these are the two standard vectors that we will be using for 0 and 1. Um, Now you might wonder, what is this funny looking angle bracket notation? So this comes from quantum mechanics, and it's called the bracket notation. So let's talk about the bracket notation a little bit. So bracket notation is nothing but writing A transpose B, where A is a vector and B is a vector. So let's say A is the vector 1, 2, 3, and we transpose it so it look like 1, 2, 3, like a row vector. And then B is, let's say, another vector 4, 5, 6, and it's a column vector. So vectors by default, we'll think of them as column vectors, and then when we transpose them, we'll make them row vectors. And if you multiply these two, you can see this is a 1 by 3, and then the second one is 3 by 1, so it'll multiply to be a scalar. And you should know matrix multiplication, so this is simply 4 plus 10 plus 18, so 32 would be the answer here. So writing long matrices can be pretty tedious, and in quantum mechanics, this A transpose B is represented in this bracket notation, A, and then B like this. So this is basically called the bra, and this is called the ket. And you can see together this makes the bracket, like this. So but all this is the bra part is a transposed vector, and the ket is a column vector. So let me clear this here. So like we said, this 0 here, this is the column vector 1, 0. If this was in the bra portion like this would effectively be the row vector 1, 0, like that. So if I was to do 0, 0 like this, what this would basically mean is that I now have the row vector 1, 0 multiplied by the column vector 1, 0. And you can see this is then basically just equal to 1. So now that we understand the bracket notation and we understand uh, the value of 0 and 1, let me remind you, just in case you forgot, it's 1 and 0. I need to see how do I erase here. Okay, there we go. And then the 1 we said is 0, 1, just like that. Now we will basically say that this, we're going to draw a three-dimensional axis just in a second, but let's say this is the z-axis, and the positive end of the z-axis will be the 0, and the negative end of the z-axis will be the 1 vector. Now, what are we going to do with the x and y axes here? We are going to create a complex plane, and on the, let's say this is the x-axis and this is the y-axis. On the y-axis, we'll put an imaginary, and on the x-axis, we'll put a real, but since we're already using this 1 and 0 notation, we will represent it with a plus sign. So let me now define a Bloch sphere. So we have a sphere like this, and we have the x-axis, the y-axis, and the z-axis. This is the 0. On the negative side of the z-axis is the 1. On the positive side of the x-axis is the plus vector. On the negative side of the x-axis is the minus vector. On the positive of the y is the imaginary vector. And on the negative of the y is the minus I vector. So if you see here, the xy plane is basically a complex plane. And if you remember, a complex plane just looks like real numbers on the x-axis and imaginary numbers on the y-axis. And you can draw vectors like 2 plus I, where you went 2 on the real side and then maybe, once I on the imaginary side. So I'm not going to try to go too much into the complex plane here. But I do want to remind you of a couple properties of the complex plane so that we can continue this discussion. So this sphere that we drew is called the Bloch sphere. B-L-O-C-H, Bloch sphere. And I want you to remember this picture. Now for the complex plane, I want you to remind you of, there are several ways to write this vector, right? One is to write this vector as the real part plus the imaginary part. So you might write like 2 plus I or something like this. The other way to write this is in terms of the radius and the angle. So let's say we have 2 plus I. So what is that in terms of the radius and the angle? Well, this side here is given by r sine theta, and this side here is given by r cosine of theta. So in terms of the polar coordinates, we would write this as r of sine theta plus cosine theta. And let me remind you, sine theta plus cosine theta is written as e to the I theta. So this can also be written as r e to the I theta. And then for the specific case of 2 plus I, you could work out what the r and the theta values would be and plug them in to get this particular form, r I theta. So this will become useful because typically when we are doing quantum computing and we are writing the vectors along the Bloch sphere, we will be writing them in this form, r e to the I theta. And so you will see a lot of times the 1 over square root of 2 type of terms will show up for the r. And theta will represent the angle along whichever along the phase on the Bloch sphere, the complex plane that we spoke about. So basically, we would have our sphere, we have our x-axis, our y-axis, and our z-axis. So let's say you have a vector that is sitting exactly between the 0 and the 1, and maybe it's sitting exactly on the y-axis like this. So this particular vector is sitting between the 0 and the 1 vectors, and what that means is that the probability that we will observe in a experiment a 0 state or a 1 state when measuring the quantum bit will be exactly 50-50. So half the time we'll measure a 0, half the time we'll measure a 1. Now if it was this particular vector, let's say that was going straight up along the z-axis, what that means is anytime we observe that particular vector, it will always be in the 0 state. And if we were looking at it in this direction, it would mean that it's a vector in the 1 state. So anytime we observe a qubit that is in quantum mechanics, when we measure it, we call it a collapse of the wave function, or the phenomena is basically that we will measure always the 0 or the 1 state. We're never going to measure partial states, right? But when we have not measured it, we may have a qubit which will have a certain probability of being measured in 0 or 1 state. So that's the wave function, or a superposition of the 0 and 1 states. So how will we write that? So the way we'll write that superposition is we'll say it's a psi. So again, now you know this is a column vector based on the bracket notation we spoke about. And psi is going to be alpha of 0 plus beta of 1 vector. And alpha and beta here basically are, in a way, the probability, not exactly the probability. The probability is alpha squared. So the probability that we'll observe the 0 state is given by alpha squared. And the probability that we will observe the 1 state is given by beta squared. So that is basically the wave function for any given superpositioned state. So let's do a more concrete example. Let's say that we have a quantum bit which is superimposed in a way where 3/4 of the time we will get the 0 state, and 1/4 of the time we will get the 1 state. So how would you define the wave function for this particular quantum bit? So well, the wave function for this particular quantum bit, 3/4 of the time we want to get the 0 bit. So we're going to take the square root of that. So that's our alpha. So square root of 3 over 2 of 0. And then 1/4 of the time we are going to see the 1 state. So we're going to take the square root of that. So plus 1/2 of the 1 state. So this here is showing us the wave function of a superimposed quantum bit, where we will see 3/4 of the time the 0 bit and 1/4 of the time the 1 bit. Let's do another example where we might see the function half in the 0 bit and half the time in the 1 state. So what does that mean? Well, we're going to take the square root of 1/2, which is just 1 over root 2. And we're going to take the square root of 1/2 again, which is again 1 over root 2. And so this is the wave function for something where we have half and half chance of observing the 0 or the 1 state. Whenever we observe the state, it will collapse to exactly being 0 or being 1. And why are we writing it like this? Because we will next talk about quantum operators like the Hadamard operator or other operators like the Hamiltonian or something, and we might do a matrix operation using that operator on the wave function on the qubit. So we can have a lot of different matrices we may multiply the front by, but this is kind of the idea here. So let me not jump ahead onto that just yet, but that is the... so these are the wave functions we have written based on the probabilities. So now you've learned about the Bloch sphere, you've learned about creating wave functions, the superpositions of the 0 and 1 states. Now I just spoke about a little bit about adding operators, and you might be wondering in the Bloch sphere when we showed a sphere, we said the chance of 0 along the z-axis here, 1 along the negative z-axis here. So if my vector is sitting here on the y-axis, or if my vector is sitting along the x-axis, either way, why does it matter? Because either of these will create the exact same wave function as far as I'm concerned with the probabilities of there being a half chance of being in the 0 state and half chance of being in the 1 state. So why do I care about the phase, which is represented in the xy plane at all? Well, that's because when you start adding operators, then knowing the exact phase will make sure that you're getting the same result each time you apply the operator. And it will help you know whether you're going towards 0 or 1 with a given operation. So even though you're not going to be observing the phase directly, you will need to know the phase as you do operations on the quantum bits in order to track your paths. So I leave it here for this particular lecture. You've learned about the phase in the Bloch sphere a little bit. We will discuss in the next lecture various operators and how you might apply them to these wave functions. And then we will talk about quantum functions and quantum gates and various algorithms that we can produce with these particular functions and what kind of benefits we can get over the classical computer. Thank you.